Okay, thanks. We had a great discussion yesterday. Hopefully you will continue to ask a lot of questions and so on. So what I thought I would start with today is to sort of slightly change the precise observable we were working with yesterday, because this new observable allows for a much simpler explanation of the basic underlying facts about Feynman diagram and how to cover the moduli space, etc. So the thing that we have here are two closed string vertex operators on the disk. So imagine that you have some closed string background, and in that you have put some D-brane or D-instanton. So you also have Riemann surfaces with boundaries, and then somewhere you have two closed string punctures.
Sorry, this
Yes.
is a continuation of that discussion, or this is a new discussion?
It will merge into that discussion very quickly. So basically, instead of considering the 4O amplitude, where we put the four vertex operators on the boundary, now we are just considering a different amplitude, which is a 2-point closed string amplitude on the disk. But it will become clear why this is a simpler object to study, and things will be much more geometric and vivid in that thing. Okay. So can anyone maybe, just to get some audience participation, what is the dimension of the moduli space here? What is the dimension of moduli space? Yeah, right, that's right.
One real?
Yes. One real, because you have two punctures, so they can move independently. So naively you have two positions of this guy and two positions of this guy, but then there's a PSL2R, which removes 3. So 4 minus 3, it's a one-dimensional moduli space. So it's like the 4O. Okay. So the one way to fix those PSL2R is to use two of the generators to fix one vertex operator at the origin. Okay. So you can use a PSL2R map to take an arbitrary configuration of these 2 points and move one of them to the center of the disk. Now you have one remaining freedom, which is just a rigid rotation of the disk. So you can use that one to bring the second guy on this line segment from 0 to 1. So that's just your one real parameter. You have this modulus of the x position of this going from 0 to 1. Yeah.
In the interior, usually we have SL2C rather than SL2R.
No, anything with a boundary, it has SL2R. So for a sphere, you will have that. On a disk, it's more appropriate to call it SU1, 1, but it's isomorphic to SL2R. So one way to see that is that you can map this whole thing to the upper half plane, where this operator O, this 0, will get mapped to the point I. Okay. So let me circle this one. So the circled guy will go here, and this guy will be somewhere here on this line segment. And if you call this plane Xi and this plane W, then the relation between them is that Xi equals 1 plus Iz divided by 1 minus Iz. Okay? So you can check that if Z is real, that is on the boundary, then this thing has absolute value 1. Because it's 1 plus I real divided by 1 minus I real. So the boundary maps to the unit circle. Z equal to I maps to the origin. And you can also check that if Z is purely imaginary, this is purely real. Okay. So essentially the moduli space is labeled by Y, which belongs to 0 to 1. Okay. So that is why the moduli space is very similar to the 4O, because that was also a line segment. So topologically, these are the same, but of course, physically very different. Now, where will the divergences be? So, okay, so we have a moduli space. Sorry, yes.
1 plus C over 1 minus including if C is I times something that's not.
So that's real.
That's real.
So then when Z is I times something, it's real. Yeah.
Can you just say a bit more about the setup itself? Because if it is just a closed string propagating, then I would have imagined it's just a sphere with 2 punctures. But
Yeah.
it's a disk with 2 punctures inside.
Yeah, so now it's like you can imagine there's a D-brane. So the closed string gets absorbed by the D-brane and gets re-emitted. So it's a 1-to-1 scattering, but in the presence of a D-brane. So there's the D-brane, the closed string comes, gets absorbed, and that gets re-emitted.
So the region on the D-plane where the world sheaf comes and collides, that's where the boundary is, and that's where the disk is, right?
Yes, yes, right. Yeah, right. Okay, so this is clear. That's the moduli space for the line interval. And again, near the boundaries of moduli space, there can be some issues. So we have y here, it's going from 0 to 1. And both near y equal to 0, which is when this puncture is approaching the boundary, and near y equal to 1, when this puncture is approaching this other closed string puncture, there are potential divergences, again due to some OPE expansion. Now, for the purposes of this lecture, I will ignore the divergences from y equal to 1, or ignore divergences from y approximately equal to 1. And the reason is that in the minimal string, that's really true. So the set of papers that we wrote with Ashok and collaborators, we were studying this specific model of string theory called minimal string theory. And it so happens that in this channel, sort of in this OPE, there are no singularities. So the integral, basically, if you write this thing as a modular integral from 0 to 1 dy, the integrand is such that y equals to 1 has no divergence. It's just a special case, so let's just go with that. So let's try to understand what happens near y equal to 0. Okay. And a particular worldsheet CFT. Yeah. So for a particular worldsheet CFT and a particular choice of vertex operators, this does not happen. But it's a special case. Of course, in the more general case, you will have them as well and you'll have to deal with it. But okay, so let's focus on the region y less than 0. So we focus on the region y close to 0. And there what is happening, yes. Yeah.
So near y equal to 1, the regeneration is the open channel.
No, near y equal to 1 is there are two closed string punctures that are approaching each other. So you literally do a OPE between those two, like a bulk OPE, right? Whereas near y equal to 0, we have to do a bulk boundary OPE. So the statement of the bulk boundary OPE is that whenever a insertion in the bulk of a boundary CFT approaches the boundary, it can be rewritten as a sum of the open string operators. Okay, so that's a statement. Okay, so that's something that we do. Okay, so what happens in this particular case is that in this minimal string, so you get an integral 0 to 1 dy f of in the sorry. So let me just say it in words. I won't. It's just a specific worldsheet CFT with total central charge 0. It has the BC ghost with central charge minus 26 and some Liouville type theory which can have an arbitrary central charge to make the total thing 0. That's Liouville, yeah. So it's Liouville plus maybe some minimal model and the BC ghost. The details are not really important, but the point is that worldsheet theory is also exactly solved. Like you know all the correlation functions is as good as a free theory. In the sense that at the CFT level, even the boundary conditions are fully understood. The bulk boundary OP is fully understood. So it's very explicit. So you can do calculations with it. Maybe was there a question online or? No. Sorry? Bosonic, purely bosonic. So in this case, there are no closed string tachyons, which is really why that y goes to 1 limit was okay. So these kind of minimal string theories have the property that there is no closed string tachyon in the spectrum. But when you have this D-brane, the open string spectrum does have a tachyon. So the open string stretched between whatever this boundary condition is does have a tachyon. And that is precisely why this thing, f of y, near y equal to 0, behaves like 1 over y square plus order y to the 0. Okay, so this particular correlation function, this C correlation function on the upper half plane in this theory has the property that near y equal to 0, it's going like 1 over y square, and you can see that it's divergent. So it's again like this x to the minus s minus 1 problem that we had last time. So the way we will deal with this is to split this integral from 0 to epsilon, and we can write dy, and here we can just write 1 over y square because this expansion is accurate in this interval, plus epsilon to 1 dy f of y.
This is the term in the OP due to the open string tachyon?
Due to the open string tachyon, yes. So this bulk operator, whatever it is, when it goes near the boundary, it produces a open string tachyon. It's equal to the open string tachyon plus a bunch of stuff, and that is why, yeah, there's the problem. Okay. Yes.
Y going to 0 is like the two, like the two vertex operators coming on top of
No. That's y goes to 1. So you see, one of them is fixed at I. That is y equal to 1, the y coordinate. The other one is moving.
So Y refers to the
Y refers to the coordinate of the second operator that is moving or sliding along that line segment.
Why is the imaginary of Z?
So y is im z, yeah, right. So z is x plus iy, and y is the imaginary part of z. Thanks. Okay, so now we have to figure out a way of what to do with this problem. Okay. So okay, let's go ahead and start doing things like in string field theory would tell us, and then we will figure out how to deal with this problem. Okay, so here is the picture again. So I'm going to draw a lot of pictures in today's lecture. So here's the vertex operator at I, which is fixed, and the other one is going sort of very close to to the origin. It's coming very close to here. Now what you do is the following. So this epsilon is some number here, okay? So I'm going to mark it kind of big, actually maybe bigger. So we have the operator at I, and we have this operator which is kind of approaching the axis, and here I will draw this epsilon here, okay? And draw a semicircle around this thing with epsilon. Okay, and what we will try to do is somehow, not exactly at epsilon, but somewhere we will cut this diagram into two parts along some semicircle, and then think of the two pieces separately. Okay, and the cutting will happen as follows. So there will be some cut at epsilon. There will be some cut at epsilon times q. I will explain what q is. Okay, and there will be this guy over here will be at some other number. Okay, so we will have this nested kind of three semicircles. There is one which is this open string. The closed string vertex operator is here, and you're kind of coming in like this, and at some point we have to do these cuttings. Okay, so now I have to explain what all these means. Okay, so first we will try to understand this region which is outside this epsilon point. Okay, so what this yellow manifold is some closed string vertex operator ending on a state in the Hilbert space of the line segment. Okay, so let me detach that piece and draw it here. So if I just detach that part of the diagram, it looks like this. Okay, so there's an I here, and there's so the stuff here I have forgotten about. So there is this. Okay. So now the best way to see what this is to actually take the log in this picture to go back to the strip. Remember last time when we were doing the state operator correspondence, there was a strip of width pi and tau, and we took the exponential to come to the upper half plane. So now let's take a log. Okay, so let's take a logarithm in this picture, and what it will become is the following. So it will become the strip, right? And remember that the position along this strip was tau and sigma, and the mapping was that z equals e to the tau, e to the I sigma, right? So that point at I is located at just in the middle at tau equal to 0, right? Because z equal to I has absolute value 1, so tau is equal to 0 and sigma is equal to pi by 2. It's like right in the middle. Okay. Now, as you come down, you are going towards this side, right? And there is this semicircle which has radius epsilon. So if you take the log, you'll have some number here which is log of epsilon, which is negative because epsilon is less than 1. Okay. So this whole picture maps to the following, that I will draw this, and then the whole yellow region is the region to the right of this, right? Because the yellow region is going to large values of mod z, so it's going to large tau. Okay, so it's kind of like a strip. So what you have done is you have taken the state, the vacuum state, perturbed it by a closed string operator, and you have sort of trying to get its projection onto some open state in the open string Hilbert space. Okay, so by the state operator map, you know, whatever the state this is, I can fill it in and put an open string operator here, because this is some state in the Hilbert space. We know by the state operator correspondence that this state corresponds to some operator inserted here, right? Which is like basically saying what is the operator that you would insert on this side to create this same state, right? So this thing is equivalent to a full upper half plane with now a new open string operator inserted here, which was not there in the previous picture, and you have I here. Okay, so that cut part is equal to just this CO amplitude. So there's one closed string operator, and this green operator represents this cut thing, right? And this green operator will be summed over, because when you're cutting a path integral, you insert a complete set of states. So this green thing really represents a resolution of the identity in the open string Hilbert space. And for each state, there is this operator. Okay. Yes? So here, just imagine that this is some state in the Hilbert space of the CFT on a line segment. And you know by the state operator correspondence for open strings that every such state can be created by a local open string operator inserted at the origin. So that's what we are using. That just stays there, right? That just going for the ride. So that's here also, and that's there here also. So that I'm not changing anything. The only thing I'm changing is that I'm interpreting this state now as being prepared by this operator, and the rest of it is what it was. So there's nothing really special going on. Like if you're familiar with cutting and gluing of QFTs in the path integral, this is pretty straightforward. Okay, so now this thing is a CO amplitude. Right? There is a closed string operator and an open string operator. So what is the dimension of the moduli space of this? So let's say you didn't start with that problem, but you just wanted to now compute some closed string I give you, some open string I give you, and you want to compute the CO amplitude. What is the dimension of the moduli space of that? That one is 0, because this has 2 positions, this has 1 position, that's 3, and then there is a PSL2R, so you have really nothing. So this diagram here has no moduli. Okay? Yeah.
So I followed you from up to there.
Yeah.
And then when you wrote the left
Yes.
picture, you're back up there, but you replaced the
Yes. Exactly. I've replaced this half disk with an operator here, because we know that that's true, right? In a CFT.
This is this bulk boundary.
Yes, 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 yes. By a sum over open string states, yes. But let's make it more explicit a bit more slowly. Okay. So now, based on what I was doing this analogy, so yesterday we were considering the 4O amplitude, and this had one modulus, and the corresponding to that is this CC guy, and we saw that this triple O has 0 moduli, and that is analogous to this CO now. Okay. So what I want to do is construct a candidate CC amplitude using Feynman diagram of this CO. So here is how you can do it. You can take a C. Let me draw the open string operators with a dot. So this is not supposed to represent the disk. This is my weird way of drawing Feynman vertices. So there is something where there's a closed string and an open string, and I have another such vertex. Okay, so closed string and open string. Open strings get joined by a propagator, and the closed string, the external closed string, and the external closed string get joined by a line. Okay, so this represents a term in the Lagrangian, which is some number lambda times phi times chi. Okay, phi is the lambda is the coupling constant. Phi is the closed string field, and chi is an open string field. Okay, so even though it's a quadratic term, because closed and open strings are on a different footing, there is some coupling between them. So this coupling in the Lagrangian is just written as a bilinear term between the closed string field, it could be the graviton or the dilaton or whatever, and this chi could be the tachyon or gauge field, whatever you want, and there is this number lambda here. Yeah. Right, so the figure right above is, this is a term in the interaction, so you bring down two of these down from E to the action. So you get two of these, there's a CO and a CO. The open string becomes an internal line, and then the C's are joined, the external C's are joined here.
Sorry, I didn't understand.
Yeah.
That's what this vertex you're describing, that transition of C to O,
Yeah.
right? By this vertex. And
Yeah.
what is this full diagram?
Yeah. So right. So we'll come to it. So what this CO amplitude was describing was just this vertex, right? But we have to construct the full CC amplitude.
Oh, I see.
So just like we glued two cubic vertices yesterday, right, using a propagator. Here you are gluing two of these CO vertices together using an open string propagator. That's the idea. Okay. So that is why this CO is playing the role of triple O, and you're gluing two of these vertices using an open string propagator. Okay. So now we need to come up with these local coordinates and coordinate charts and so on for the vertex. Yeah.
What are these circles?
These are just operators. O, like 3 O's, open string operators. You mean these circles or these circles?
The left one on the left.
These are not circles, this is O. O1, O2, O3.
But why does it, the second one, why does it correspond to the one you showed just recently, this one?
It corresponds to the sense in the sense that it has a zero-dimensional moduli space. That's all I meant.
But why there are 3 O's?
Well, we saw yesterday, right, that there are these cubic Feynman diagrams. So there's a 3O amplitude, 3 gluon amplitude. So that's what this represents.
What about the 4 O's?
The 4O will be the 2 to 2 gluon scattering amplitude. Right, so this is more complicated. This line is simpler. This is a building block for this. So this CO is a building block for this guy. Okay. So now we need to have a prescription for coming up with this lambda. Okay, how do we write this lambda? Because generally this internal line will be off shell. Right, in Feynman diagrams, internal lines are off shell. So you need to now come up with a prescription of writing down a CO vertex where at least the O part is off shell. Okay, so then again you need to introduce local coordinates and so on and so forth around this open string puncture. Okay, so this motivates the following. So this here I can write, right? Okay.
So
Yeah.
you can then the vertices that you are reading off, I should always read them off from genus 0 diagrams?
No, no, no.
Because Feynman rules, I will do all the loops and such.
Yeah, yeah, yeah.
So I don't want to overcount that, right?
But the thing is that at loop level, you can have these finite counter terms, right? So you can think of the things that you will need to add at loop level as some finite counter terms that are needed to be there. So even when you go to higher genus, there are missing parts of moduli space which you need to write.
Right, but as a bare Lagrangian, I just read off the vertex from.
Yeah, so if you just care about the tree level, then of course only the sphere will.
But what I'm saying is that I can read them off as from the sphere.
Yeah.
And just do the standard quantum field theory things that I do with counter terms and everything.
Yeah.
And then that should give me the perturbative corrections to that, right?
Yeah. Except you will find that when you do that, for example, when you try to calculate a one loop amplitude, that it will not match with the moduli space expression unless you correct the coefficient that you had at tree level.
So these vertices will get corrections from that.
Yeah, from higher genus, yeah.
Why I didn't understand, sorry. I thought all the vertices.
So that is the weird thing about these theories, that when you go to higher genus, that the lower order vertices, if you glue them in all appropriate ways and do the sum over the Schwinger parameters associated to them, you don't cover the full moduli space of the actual genus G Riemann surface that you are trying. So there is some missing space, and that missing space you just think of it as correcting the coefficient of that, of the tree level guy. But okay, but let's go to then understanding the CO vertex, the CO interaction vertex. Okay, so the C in our case, it does not cause any problem, so the C will remain on shell. Okay, so C remains on shell, and for O, we need to have some local coordinates.
Just because I'm sort of missing the global.
Yeah.
So if you started with the disk amplitude with two closed string
Yes.
insertions, there is a divergence and
Yes.
this corner, and it's to be interpreted as a infrared open string tachyon divergence.
Yes.
Is that correct?
Yes. Yes.
And after doing all this, I mean, you'll still be left with that divergence.
No, no, no. It will be finite. We will see.
I see. So the theory has an open string tachyon.
Yeah.
In the end, the physical answer or whatever.
Yeah, for this thing it will be finite. Because the idea is that you see, when you have even a tachyon, there's nothing wrong in writing the propagator as 1 over p square plus m square. So if you're thinking from a field theory point of view, and you're just doing perturbation theory, you're just doing perturbation theory about the maximum of a potential rather than the minimum. And that's fine. So it's true that certain kind of partition functions and so on will have some divergences. But here we are talking about some correlation function. So it's true that it might have some imaginary piece or something because of this tachyon, but it's finite.
I see. So this is because you will resum you do the mass denormalization, correct?
No, 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 no. It'll become clear. Just bear with me. So we have this. So let me draw that picture here again. So we have this closed string operator at I and this open string at O, right? And remember that this open string operator lives naively in some unit half disk, which we can call the W plane. Okay, so in the W plane, there is a unit half disk, which is the native resting place of this open string operator. And that's like, this is the operator, this is the state it creates. And yesterday we were discussing about maps. So we have this Riemann surface, and we need to cover it with some open sets. And here is the open set that will cover it. And here, this will be 1 over lambda. So so W is just lambda times Z. Okay. So this is the choice of local coordinate. The local coordinate being W near the open string insertion. So this is the analog, like yesterday we had this function, right? W was 2 alpha z divided by 2 minus z from yesterday. So today I'm just picking this more simpler function. Okay, so you have a half disk of radius 1, and when you do this rescaling by 1 over lambda, it ends up like a tiny disk here. Okay, so that's the choice of local coordinates. And then my lambda there, that lambda is just the expectation value of C, the closed string vertex operator, placed at the point I, times the open string vertex operator. So let's call that O, okay, but conformally transformed with this F. So F circle O at 0, okay, where F is the thing that maps W to Z. Okay, so F of W is, W over lambda. Sorry? So right now I'm just taking this to be on shell. Otherwise you would also need some open set around this guy and need some coordinates for this.
If I wanted to put this in the action, I would want
Both to be off shell. But a special case of off shell is on shell. So for that, like, you're right. So in principle, I should have some disk around this and then have some other conformal transformation. Okay. So the idea is the following, that you have this Riemann surface. This green guy is off shell. So the correlation function will depend on the local coordinate chart on this, around this green puncture. And this is the state operator kind of diagram for this guy. And you choose a specific map with this lambda parameter in it. So you think of lambda as a large real parameter. Okay, good. So that's what we have right now. So we have defined the CO interaction vertex. Here, we were supposed to take two of them and join them together. So the job of the CO interaction vertex is done. That was it. Okay, sorry. Yeah.
That lambda defined in W equal to lambda Z. Why is it the same?
Let's call this. Let's call this G.
Okay, so that G equals that, right?
Yeah.
Okay, thank you.
No, that's my bad. That's a bad notation. Yeah, the G is the coupling.
Okay, that makes sense.
Yeah, thanks. Okay. So now, to be faithful to this picture, we are supposed to take two of these CO interaction vertices and glue them together. Okay. So actually I moved it too much up. So let me draw two of them. So I have I here, and then 1 over lambda green dot here, and then this is shaded. And then there is a second copy of this guy, which is this 1 by lambda shaded and I. Okay, so I will call this Z and Z hat. Okay, so there are two open CO interaction vertices that we have drawn like this. Okay. Yes.
This is still the situation where analytic continuation momentum will get rid of divergence, right? Like when it's an amplitude.
Here actually, I already wrote that 1 over y square. You see, there is no momentum in the exponent anymore. So already, sorry. Yeah, but I specialized to the case where we have a D-instanton. So this disk boundary condition that we started with, I am assuming that that's a D-instanton boundary condition. So then there are no momenta.
How about the closed string momentum?
Yeah, so the closed string is not appearing in the bulk boundary OP, right? That's not participating.
Oh, okay.
Because you see, whatever the closed string operator is just went into the open string tachyon. And the open string tachyon is not carrying the momentum.
But this is really a place where you need this.
Yeah, you need some other rule to, exactly, come up. Yeah. Okay, so we have two of these CO interaction vertex. CO interaction vertex number 1, CO interaction vertex number 2. Okay. So what we are supposed to do is the following, that we are supposed to glue them together somehow, right? That is what this is. There is one CO interaction vertex here, some CO interaction vertex here. We're supposed to glue them. So the gluing happens via this so-called plumbing fixture. Gluing happens via that's just some name that people have given it. And what you do is you make the following equation. W prime equal to negative Q. Sorry, I used hat, so I'll use hat. W hat equal to negative Q, where Q is a real parameter belonging to 0, 1. Okay, so Q is just a real parameter. So remember that there is this Z plane, so correspondingly there's a W half disk, and corresponding to this Z hat there is a W hat half disk, and I am gluing by using the W hat coordinates according to this relation. Okay, so let's see what happens. So first of all, note that the map minus Q over W maps upper half plane to upper half plane. See, because if W is in the upper half plane, 1 over W goes into the lower half plane because it changes the angle, and then but the minus sign puts it back. So that is why there has to be this minus sign for W and W hat both to be in the upper half plane. Okay. Okay, so that's one fact. But now let's see geometrically what's happening. So in the W plane, I have this unit half disk. In the W hat plane, I have a unit half disk. Okay. Let me go in the W plane from 1 to square root of Q. Okay. So the importance of the square root of Q is that when W, absolute value of W is square root of Q, absolute value of W hat is also square root of Q. Okay. And now what I will do is to take this shaded region which is outside. Okay. So take this kind of half annulus and see where it goes into the W plane. You know, try to push this shaded into this. So what will happen when W hat is equal to 1, W, the absolute value of W will be Q, which is less than square root of Q, because because Q is less than 1, right? So you will get this thing, right, which is shaded. Okay, is that reasonable? Okay, so what this does is that it takes this half disk between 1 and square root of Q and puts it between square root of Q and Q in the W plane. So you see now we are starting to get pictures that like that, something like that, where you have these kind of nested semicircles going on. But let's really see what it means. So this equation written in terms of the Z coordinate now. So this is what was happening in the W plane, but in the Z coordinates this is lambda square Z hat equals minus Q, right? Because W was lambda times Z. So this is saying that Z times Z hat equals negative Q by lambda square. Okay, is that okay?
Sorry.
Yeah.
In here, we want to glue the two Z planes in some
Yes.
fashion.
Yes, exactly.
And
The Z and the Z hat plane using this relation. Because the Z plane was the CO interaction vertex, the Z hat plane was another CO interaction vertex, and you want to glue them. The point is that the gluing, you should not try to write directly in the Z plane. You should first start with these W planes where the pictures are very simple. You have these just half disks and so on, and then try to interpret what is happening in the Z plane. Okay, that's the idea.
And the reason why we are doing this is because we want to compute this CC kind of.
Yes, exactly.
thing, right?
Yeah, the ultimate goal is to compute the CC amplitude.
Yeah.
We have realized that from 0 to epsilon we need this kind of Feynman diagram, This Feynman diagram requires gluing, and now we are doing the gluing.
Yes, and also with the fact that O is off shell,
Yeah.
where is that in this? Where is that?
That is there in the fact that this G will depend on the F. Because you made a choice of a local coordinate patch F. Like yesterday, we had this F1, F2, F3. And we saw that if O is a dimension 0 primary, then the G will be independent of the F. But now, because the O is off shell, the G will depend on the F. In particular, it will depend on that lambda. Right? Lambda was an arbitrary fake parameter. And so this G is a function of lambda. Okay? Yeah. Yes.
Just if I can go back to your first picture.
Yeah.
So you have one closed string operator nicely
Yes.
sitting at I.
Yes.
The other one is close to the boundary.
Yes. Yes.
Now you took the yellow part
Yeah.
and you mapped it nicely
Yes.
here.
Yeah.
And the other guy
हाँ.
is roughly the part close to
बहुत
the
छोटा है अभी हाँ.
the
Right. Yeah.
part, right?
Right.
And
Yeah. But how will it come? It will come. That's exactly the next point. Exactly the next point. You see, you have this relation now. Yeah.
So, just as you said, you want to split the model into Feynman diagram.
Yeah.
The 0 to epsilon is this Feynman diagram.
Yes.
What is that other Feynman diagram?
So that is just finite. So the interpretation of that, like we had a contact 4-point function, right? So in the 4O case, the epsilon to 1 minus epsilon region, that number just gets assigned to a new interaction vertex in your thing. So that would be like a new term in the Lagrangian, which is phi phi.
Just 5 pi.
Just phi phi with a new number in front of it. Right, exactly. Okay, so now coming to Sandeep's question, what is really going on here? Okay, so there is some cut and paste we need to do, and the cut and paste will happen in these planes. Okay, so you see ZZ hat is equal to minus q by lambda square, which means again the square root of this quantity is an important thing to consider. Okay, so let me delete this part. Actually redraw the whole thing. And I stop at, in this plane, I stop at square root of q by lambda. Okay? So that's where I stop. So the vertex, remember, the vertex does not change. The vertex was at, just really need some different ideas here, how to draw. So there was this curve at 1 over lambda. So I will follow the z plane a bit deeper than the vertex to square root of q by lambda. Okay, and inside this, what I will do? I have the second plane. Let me draw the same picture here. There are two copies. Okay, 1 by lambda, and then square root of q by lambda. Okay. Now this gluing means this z hat region, which is the large z hat region, will get sucked into this whole small space here by this inverse map. So the gluing will happen on this thick circle, on this green circle that I was drawing, right? And this whole region outside, by this identification, will get sucked in and go here. So that will reproduce the green cut where we were cutting, and it will put this I where? So z hat equal to I implies from this equation z equal to I q by lambda square. Right? Z hat equal to I is a minus sign, this I q by lambda square is very small. Okay, so this is the y, right? So y, z, the imaginary part of the second operator was the y modulus. So from this thing we conclude that y is q by lambda square, which belongs to the interval 0 to 1 by lambda square, since q belongs to 0 to 1. Okay, so q belongs to 0 to 1, so this goes from 0 to 1 by lambda square. So your epsilon is like 1 by lambda square. Okay, So that is why this choice of this lambda in this map, because it's big, determines the small region in Y in which this gluing is happening. Okay, so that's what you do. So in fact, maybe here I should have not written epsilon, because epsilon is 1 over lambda square. So let me go back and correct this picture. Yeah, so you see this picture was not quite right, and I deliberately didn't want to fix it in the beginning, but this is like square root of epsilon and so on. So but that is the correct picture. Okay, square root of epsilon. There is another one at square root of q times square root of epsilon. So let me now write it in terms of lambda. Okay, so there is 1 over lambda, square root of q by lambda, and then q by lambda, and then q by lambda square. Okay, so the region sort of up to square root of q by lambda is the z plane, and then everything inside that is the other one. Okay.
Why are there other circles?
I'm just drawing here, right? So there are 2 circles here, okay, and 2 here. This one is glued, so the total there will be 3 circles. So that's 1, 2, 3, and this one I'm just drawing to indicate the location of the closed string puncture at q by lambda square, just to see where it is. In fact, I should draw another one where this thing is coming down to 1. Right? That circle will pass through I. Okay. So let me now improve a bit more on what we are doing. Sorry.
So is it like top I is the closed string thing, and when you start coming down, you have an open string state, and then there's another circle that just tells you how the 2 manifolds are joined.
Are joined.
So there's no insertion on that in between.
We'll exactly come to that. So let me just now, I think it's great that people are just anticipating the next thing I'm going to say. Yeah. No, in the vertex only the lambda appears. So let me now try to explain. Like, so let's draw more pictures. So in particular, this picture, should have just had log of 1 over lambda, right? Because the vertex just stops at 1 over lambda, right? The Q really comes in the gluing. You see, when I was talking of the CO vertex, I only introduced the lambda, right? There was no Q. So in the vertex, so what you have is the following picture. Just take a log of this whole picture, okay? So there is one vertex, closed string vertex at tau equal to 0. Okay, that's mod z equal to 1. You go in, that means you are moving to the left. The first circle here is the log 1 over lambda, right? So this part of the strip is a vertex, CO vertex. Okay, then we have some region up to, so there is some point here which is log of square root of q by lambda. Let me not draw that. Then there is a log of q by lambda. Okay, and then this guy, the other closed string operator, is sitting at log of q by lambda square, right? That's correct, right? I mean, I'm just mapping those circles that I drew to vertical segments here, and this thing is the second vertex. You see, in the vertex, the distance between the closed string and this boundary is lambda, or log 1 by lambda. So here the log, if you take the difference, the log q will cancel, and the amount of distance here is just again log of 1 by lambda, right? So what is this middle region? This middle region is the open string propagator. With proper time, how much? We just have to take the difference between this and this, which is log q. Okay? So here you see that the lambda is a property of the vertex. It kind of sets the width between this closed string insertion and this open string where you're inserting a complete set of states, right? And the Q is telling you how big the strip is with which you are gluing. Okay? So that is why this Q is a nice parameter to have, because it's directly related to the amount of time that this open string propagates. Right? And note that this, right, so that is really the picture to have in mind for the CC vertex. So you have the C and the C that were here, and when this second C goes very close to the boundary, that means in the strip they are very far apart. So when they're very far apart, when do you start measuring very far apart? When y hits 1 over lambda square. So if y is close to 1, then you don't have this picture, you just have a direct CC vertex. As you take the y down and it enters this interval, you start exposing some of this propagator. Okay? And as q goes to 0, this propagator is infinitely big. Right? The size of this is log of minus log q. Right, so if there was a negative energy state here, propagating, it would get enhanced. That's the tachyon giving the infrared divergence. Okay, so now let's interpret that dy over y square from this perspective. Okay, so this integral from 0 to, actually that, so epsilon is 1 by lambda square, so that is correct. So let me define here. Epsilon is 1 by lambda square. So 0 to epsilon dy over y square, right? So yesterday I was saying that you have some moduli space coordinate, but you should really change variable to a good coordinate, and the good coordinate here is q, right? Because q is representing the proper string, open string proper time. So change coordinates, change variables from y to q. Okay, so what does that give? So q is y divided by epsilon. So that's integral from 0 to 1 dq 1 by q square, and y is epsilon times q, so there's a 1 over epsilon. Sorry? Sorry? That's here. See, because when we suck this z hat plane into this, we got a thing here. So the gluing gives you a relation. So basically, see what this is saying. This is really making precise the fact that certain parts of moduli space are really Schwinger parameters. So this region of the moduli space between 0 and 1 by lambda square should really be interpreted as a Schwinger proper time of this open string. Okay, that is another sort of lesson from here. Okay, because the moduli space, contains within it these proper time propagations of open and closed strings. But how you expose them is a matter of certain amount of craft, which we did here.
Sorry, why the two shaded regions representing closed strings?
Not closed string, they represent the CO vertex. So this part of the graph represents this thing that I was drawing. There's a C and an O. It represents this G that we had. Or in that plane, you see there's a C and an O, and that's it. Right?
So it's like the intersection between the unshaded region and the shaded region that's taken that's separate.
The vertex is just everything to the right of this. The whole thing is CC, and you have divided it up into CO, a propagator, and a CO, right? Where did that diagram go? So this thing should be interpreted as now as CO, propagator, okay, and CO. So this part is this part, this blob here is this whole thing, and this whole thing is this blob.
So the one at infinity is like a closed string.
At infinity is just vacuum. The closed string insertion is here. They are marked by these x's. Right? So at infinity, when you don't insert anything, you just have the vacuum state coming in. That vacuum state gets acted upon by this closed string operator. So over here, you will generate some mess in the Hilbert space, right? Like there will be some general state in the open string Hilbert space, which you can express as using the completeness relation as a sum over some basis, some complete basis of eigenstates of the Hamiltonian. And once you have that, this propagator will give you the phase factor that you need. So think of this as like the ket, the propagation, and then the bra, right? That's it. Yeah.
Isn't epsilon q over lambda square?
No, epsilon is just 1 over lambda square. See, that's very important actually, because see, what was epsilon? Epsilon was where we cut off the moduli space in Y. That is the fundamental definition of epsilon. Now, what is this telling us? This is telling us that Y is q over lambda square. Q is a parameter from 0 to 1. So you see, as q goes from 0 to 1, the Y goes from 0 to epsilon. You see, because this is still covering some finite region of moduli space of codimension 0.
As q goes from 0 to 1, y goes from
It's just linear, right? From 0 to 1 by lambda square.
1 by lambda square, yes.
So that is 0 to epsilon. That's exactly 0 to epsilon. Right?
So now that I have,
Sorry?
now that I have this
Yeah. So,
time parameterization.
so how would we now fix this, right? Exactly. So now let's write q, define a new variable q, which is basically this, this thing, q e to the negative tau. Okay. So tau belongs to 0 to infinity. And this integral becomes integral 0 to infinity d tau e to the tau. Right? dq by q is d tau, 1 by q is e to the tau. So you get d tau e to the tau. Okay? That is, again, it's just divergent, right? It's not telling you much. But now you realize that where this is really coming from was the fact that, you know, this thing was really supposed to be 0 to infinity d tau e to the minus L0 tau, where L0 is the Hamiltonian which propagates you by this time t, right? So if L0 was positive, then this thing would have just been 1 over L0, right? Just the simple integral. Now we have a situation where L0 is minus 1 because of the tachyon, this open string tachyon that is propagating in this. Okay, so you say this is bad because L0 is negative, but this is still okay. Okay, so you really forget about the Schwinger time representation and just say that this thing is supposed to be the open string propagator. And I know that this is equal to, sorry, there is also a 1 over epsilon. So it's equal to 1 over L0 times epsilon, where L0 is minus 1. Sorry, 1 over epsilon. So that is how you get a sensible number from the region between 0 and epsilon. Because you interpret this integral as 1 over L0. 1 over L0 is the propagator. And you know that in this case, this open string tachyon has L0 equal to minus 1. So you have a minus 1 over epsilon. So we managed to get some result.
Just ask you,
Yeah.
in string field theory, you would set up some propagator so that you would actually get bubbles.
No, the propagator is just defined by the quadratic terms. You see the string field theory.
Yes, but I'm just asking,
Yeah.
are the quadratic terms such that they give you whatever, minus 1 here?
Yeah, it will. Sorry. Yeah, L0 is the propagator. So you will have a, you know, like in the kinetic term, you will have things like e to the minus h times phi square. So the propagator will be 1 over h, where h being the scaling dimension of the field.
Thank
Yeah. Yeah.
This process here, let's say I had maybe going back to this momentum.
Yeah.
So if I have some closed string coming in,
Mhm.
it's a momentum.
Yeah.
Then the momentum is conserved at these vertices, right? So this middle line should also have some.
Not if you have a D-instanton. See, in the D brane, in the perpendicular direction, the momentum is not conserved.
I see.
So that momentum just goes into the residue of the pole, and the power of the pole is actually independent of the momentum. Right, so that's important because the D brane boundary state has all momenta, so it can just absorb the string, like we were discussing. Yes, right.
In the D0
Yeah, yeah. So in the D0 brane, the omega is conserved, but the transverse momenta are not. So here you have a D-instanton, so nothing is conserved.
and so this is basically the propagator of the tachyon at zero momentum, right?
Yes,
1
yeah.
over p square
Plus m square, but the p square is 0, right?
and
Exactly.
m square is negative.
Yes.
So minus
Exactly. Yes, right. Okay, so let's recap what we did. It's very important to separate. Sorry, go
From
on.
this point of view, this epsilon was because we got minus 1 over epsilon.
Yeah.
That was what from this point of view?
So no. So we were trying to do an integral over y from 0 to 1, right? We chopped it up from 0 to epsilon. Epsilon to 1 we have not yet done.
Yeah.
Okay, so that you will do in some way of doing it. And you will do it, and you will find that this minus 1 over epsilon cancels in the end.
No, but in space-time action, this epsilon appears in front of the quadratic term then?
Yeah, it will. It will appear because of the way you are defining things.
Yeah. That's the role of the epsilon, so that's why it worked.
Actually, sorry, no, let me take that back. This epsilon will be in the vertex. So you see here you don't just have a propagator, you also have these CO vertices. And the vertices, as I was answering that question, depends on this f. And that f has the lambda which is related to epsilon. So the square root epsilon is like lambda which will come from the vertices. So this 1 over epsilon is coming from the vertices.
So it's G square.
G square, yeah, right. Well, there will be a G square kind of scaling, but this epsilon is like, you see, to define the vertex, you needed to introduce an epsilon, right?
Yeah, but in whatever choice I made, the final, my coupling constant was 1 over square root epsilon, right?
You can say that, yeah.
When I write down the action,
Yeah.
right?
Yes, you will write, yeah.
Write CO vertex with 1 over square
Yes,
epsilon.
yes, exactly.
Then with the propagator
Yes.
applied with minus
Yeah.
1, I get that.
Yeah,
That was fine.
right.
But this constant will be dependent on the scheme of the coordinates of Raghu's.
Yeah, this will depend, of course, because the whole Lagrangian depends on the scheme of the coordinates you picked. And actually this answers a question that Omkar was asking me yesterday at lunch, that why these string vertices are so soft. Okay, so here you kind of seem to get a bad result, why the vertices are sort of suppressed. Here it's enhanced because you're dealing with a tachyon. But you see, if the thing that was propagating had positive mass dimension, then this vertex will give you negative powers of lambda and hence positive powers of epsilon. Okay, and remember that this lambda is related to the propagation roughly from here to here. Okay, so that is why, already in propagating from here to here, you are suppressing all the positive L0 states, right? So only kind of some of the light states kind of matter in this. So you can also see that if there were no tachyons or zero mass states, there was no need to introduce this lambda in the first place, right? But even if you do introduce it, all the heavy states are already suppressed because you're doing this amount of propagation in the vertex part, okay? Just in the vertex part. So the vertex parts have exponential of L0 factors in them, minus L0 factors.
Raghu, can you again explain this argument that you said that a bit slowly why these things are?
They are suppressed because you see here you got a large answer from the vertex, from the square of the vertex, because L0 was negative for this tachyon. You see that F circle O, the conformal transformation, is F prime raised to some delta, right? And F prime is, it's just related to lambda or 1 by lambda. I can't do it right now, but okay. So that's the final result. that you can really calculate a finite number even though you had this divergence from 0 to epsilon by doing this process. Okay? And I really want to emphasize this picture, that you have some CO interaction vertex plane, some other plane, you have two vertices, and this plumbing fixture kind of maps big regions in one plane to kind of small regions in the other plane. So this whole thing kind of gets sucked into a small region. Okay? And in the end, those open string operators are not really there because you're summing over them, or you're inserting a complete set of states or something. Okay? And then you can recursively build more and more vertices and keep going. You know? So this is the simplest kind of example.
But I'm so sorry.
Yeah, yeah.
This is the global picture.
Yeah.
Okay, you began your lectures by saying there were various infrared kind of problems.
Yeah. Yes.
So what was the infrared problem for two close string vertices?
Here the infrared problem is that if this white strip becomes very long, which is infrared, the propagation of the tachyon will give you a divergence. Because the Boltzmann suppression is by e to the minus tau L0, and L0 is negative. So that's the infrared problem here.
That's the infrared problem.
Right.
And in the end, you are still seeing it with this 1 over epsilon. Yes.
There is a minus 1 over epsilon, but the point is we have not yet done the full integral, because remember, sorry? Yeah, because we have not yet added, so the full amplitude, remember, was 0 to 1 f of y dy, which we split as epsilon to 1 dy f of y, and then now the answer we have gotten is this plus minus 1 over epsilon, right, for the other part. This integral is just completely finite, we can do it. And you will find that this is something finite plus 1 over epsilon, and then plus minus 1 over epsilon. So this will be the structure of the answer.
Where is that 1 over epsilon coming from?
It will just coming from doing this integral, because f of y is an explicit function. You see? So that I can just write down and do the integral, you will get that.
But earlier you said that there is no similarity between two closed string.
Yes.
Closed string interacting with the degree and going to the degree, right? So there is no.
I said that there is no singularity coming from the y goes to 1 region. So y goes to 1 region is completely fine here. It's this lower limit which is problematic.
This epsilon. Right?
Sorry?
Epsilon need not have been small.
Which epsilon?
Would have been half, right?
This epsilon? Yeah. Yeah, yeah.
Half. So there is no 1 over epsilon not necessarily singular.
Yeah. The only thing is that if you kept epsilon finite, you see, epsilon is the strip, that shaded strip between the cross and that vertex. If epsilon is not small, which means that strip is not very big, then all the heavy states will also propagate. Right? You're really supposed to insert a complete set of states there, not just the tachyon. So you will have to do the complete sum over a full resolution of the identity at that cut, and that will contribute some positive powers of epsilon. So if epsilon was just 1/3, you will get contributions like 1/3 to the delta, sum over all delta. Yeah. Yeah.
This is a case where if you had naively tried to compute the amplitude, you would have got an infrared divergent answer.
You'll just nonsense, because this f of y is going like 1 over y square as y goes to 0.
But now when you think about it correctly in close to infinity,
Yeah.
that divergence cancels because you can interpret 0 to infinity d tau e to the tau
Yeah.
as equal to whatever you did.
Yeah, minus 1. Yes, yes, exactly. Yeah, right.
The way
Yeah.
Ashok sometimes says it is that, maybe,
Yeah.
paraphrasing, that when you have a modular space integrals,
Yeah.
that is really mimicking like the Schwinger parameter.
Yes, 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 yes.
Sometimes it doesn't make sense.
Yes.
In particular when the states are massless.
Right, exactly. So when it doesn't make sense, then you actually use the field theory. Yeah, exactly, right, yeah.
So this is about changing that.
Exactly.
Parameterization.
Yeah, so you don't use the Schwinger parameterization, but use just the field theory propagator, 1 over p square plus m square.
So very ingenious. You use the worldsheet, even though the worldsheet breaks down.
Yes.
You use the worldsheet to construct the string field.
Exactly.
Then you discard the worldsheet.
Or you don't discard it actually.
Sort of okay, you obtain the
I've discarded it only from 0 to epsilon, right? The epsilon to 1 integral is still being done by the worldsheet. Yeah, yeah.
Okay.
So if you wanted to,
So your last thing.
Yeah.
And it didn't matter how you chopped up these diagrams and which maps you used.
Yeah, it won't matter in the end. Yeah. Yeah. The only thing is, like, if you didn't take epsilon to be very small, then your life would be complicated because you'll need to do some infinite sums.
yeah.
Yeah.
So if you did, then how is it simply? So this is what I wanted to ask.
Yeah.
If I want to compute this CC,
Yeah.
let's say, right, in this way.
Yeah.
I will just do this chopping off in this way.
Yeah.
And then some more infinite thing.
Yes, 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 yes.
Right? And then, this can
Well-
is also natural. So then there will be epsilon hanging around. That
No, no,
answer?
in the end, the epsilon is not there, right? Because when you add everything up, the epsilon went away.
Exactly, exactly. But so should I first of all organize this sum as a separate tachyon contribution and the rest of these things which don't have any problem?
No, no, you don't have to. See, the problem is that from 0 to epsilon, you're also integrating f of y, right?
Yes.
Whereas I just replaced f of y by 1 by y square. So it was at that step where I was too quick. So if epsilon was really finite, you would really need to this whole integral carefully. You know, so it will not just be minus 1 over epsilon anymore.
No,
See, if epsilon was 1/3,
the way I was thinking of this is that you fix epsilon to whatever.
Yeah, yeah. Yes,
And then you do this, right?
yeah,
Then you write an answer
yeah,
which is the sum over infinitely many states.
yes,
Each of which will have some contribution coming from the propagation.
yes,
Right?
yeah,
And the other piece from epsilon
to 1,
1,
yeah.
that will not have this sum.
Yeah, that will not have the sum, but it will depend on epsilon.
It will depend on epsilon.
Yeah,
Right? Okay, so at this stage I still feels like I have to do infinite sum.
yeah.
Now, what by taking epsilon into 0, how does this simplify?
So it simplifies because that sum over infinite thing collapses to just one term,
Because all
which was a
positive powers of epsilon
go away. So when you take epsilon to 0, the second part simplifies a lot because it only represents the tachyon and the massless states.
So this is like, the final answer, which is supposed to be independent of epsilon.
Yeah.
If I wanted to check it, I will better perform this sum.
Yes, yes, yes.
But given that I am sure that this is not going to
Exactly.
depend on epsilon, I might as well take epsilon to 0.
Right, right, exactly,
And then
exactly,
obtain
exactly right, exactly right. And this thing, this epsilon, this part from that x to that cut is called a stub. So you've added a stub to your vertex. Like in principle, you could have just stopped the vertex at tau equal to 0, right? So you added kind of a stub to it, and that stub of length log lambda suppresses the propagation of heavy states in the vertex. So the Witten vertex actually is not like that. The Witten vertex kind of cuts it right there, which is why he can just do cubic interactions and just do everything. But his vertices are a little bit singular in that sense. So when you add these stubs, you see you're not able to cover the full moduli space y from 0 to 1 just using the Feynman diagram. You only covered it from 0 to epsilon, so there's a missing piece. And that was because of the stub, right? The stub is kind of like an irreducible part of the propagator. In some sense, if you think of the whole thing between the two x's as an open string propagator,
So stub, you are calling that shaded region or the middle region?
the shaded region.
From the vertex, the additional part.
Yeah, the additional part, yeah. So this part is called the stub. But you see, in principle, you could have taken the full propagator length to be the two stubs plus this log q. Right? That's also some just open string propagator, right? But here what you're saying is that you will take some part of that and put it into the vertex, and then only consider this part as the propagator. And what, yeah,
Sorry, so if epsilon goes to 0, the stubs become larger and larger.
larger and larger, but
How does
yeah.
it follow then that the massive stuff can become
Because you see,
propagated, right?
the stuff has to propagate from here to here.
So
Yeah,
they
yes,
just drop
exactly,
out.
exactly, yeah.
I see. The vertices.
In the vertices, they drop out, yes. Which is what Omkar was asking yesterday. How are the vertices kind of so soft? That's what that means, yeah.
The previous states drop out because it's like exponential minus L0.
Yes,
times,
times this stub length.
And what about so
Yeah.
So the master state doesn't lead to IR.
There are those, I have not yet discussed them. So there are also some L0 equal to 0 modes in this particular minimal string setup. So that is the next topic.
And is it like a general theme in string theory that usually the amplitude will be integrals over moduli space in string theory?
Yes.
Where you can't decompose the diagrams into like propagators and contact things. And so yesterday also you had like an epsilon where you decompose the moduli space into like propagator things and contact things.
Yeah.
So that's like a general.
Yeah, that's a general fact that you can always split up the moduli space like this. In fact, Ashok says that in thinking about the SFT diagrams is sometimes the best way to think about moduli space. Let's say you want to do a calculation with some genus 3, 4 punctured sphere or something. You don't understand the moduli space, it's very big. But you understand Feynman diagrams and vertices, so you can recursively build up the whole degenerations and everything. So even in terms of understanding Riemann surfaces, once you have some theorem that these Feynman diagrams build up the appropriate Riemann surface, it's much more efficient from a physicist point of view to understand the moduli space using these Feynman diagrams. Right? How many propagators are degenerating? What is the topology of the Feynman diagram? Things like that.
This is sort of complicated by this fact that Abhijit was finding out that, or you were finding out that if you go higher and higher to Q, these vertices get corrected in order to cover the full modulus.
Yeah. So what you will find is that at some genus, the lower order Feynman diagrams will cover some part, all the boundaries at least. See, the boundaries are the more complicated part. The bulk is kind of the easy part, right? Because there are no divergences there. Some finite portion that's just there and it's finite and that you deal with. The hard part are really these boundaries, right? Which is why this Deligne-Mumford compactification of the moduli space was such a big achievement by mathematicians, because they really understood what the boundaries are, what are the missing nodal Riemann surfaces you need to add, and so on.
Sorry,
Yeah.
I haven't understood that comment then, but the idea is that this finite part, this contact kind of term,
Yeah.
is corrected order by order.
Yes. It will get corrected order by order.
You can't from the contact term soon with field theory propagators generate.
Not the tree level one, no. At least not, yeah.
And is it that the contact diagram here is like the trivalent can be thought of like a sphere with 3 things and the correction is like a torus with 3 things and a higher genus. The contact,
You mean for this one or the 4O?
like the general like
So here the contact diagram will be just I can write it as some G prime, phi 1, phi 2, right? Phi 1, phi 2 are closed string fields, and G prime will be the integral from epsilon to 1 dy of V1, V2, suitably conformally transformed.
What's the utility of the field theory, which is supposed to allow us to compute non-perturbative, etc. kind of things? If it's coupling constant, the contact terms have to be, corrected order by order.
No, it's even worse, because even at tree level, you have infinitely many terms in the Lagrangian.
Infinite number of terms.
Yeah, so that is why, this whole SFT framework is just perturbative. It's perturbatively allowing you to deal with infrared divergences, that's all.
That's all. It's
Right.
not something you can
No, it's because at least not in the closed string theory. See, that is one of my sort of motivations to study string field theory, is because even today we don't have even the classical equation of motion, for this Lagrangian. This is a Lagrangian that you're writing some phi cube, phi 4, phi 5, phi 6, phi 7 up to infinity, even at the classical level. How are we supposed to understand, non-perturbative classical solutions to these set of equations? We don't forget about writing a Lagrangian. We don't even understand the organizing principle, how these terms should resum, what is the analog of diffeomorphism invariance or gauge invariance that will constrain the terms we write down? Or, is it like a metric on some crazy fiber bundle, whatever, or what is the dynamical object? We don't even understand that, right? We understand it like sort of field by field, like a few low-lying fields, there's a metric, there's a B field, but the whole tower, what is the structure that it's representing? What is the algebraic geometric structure that it represents? Like we know for gauge theory, it's principal fiber bundles. For GR, we know it's like differentiable manifolds. What is that in classical string theory? Forget quantum.
So in classical string theory, all these coefficients do have G
Yeah, they will have the appropriate power of G string, like for higher point vertices. Okay, we are already at 12:30, so I don't know if it makes sense to start something new.
Because you only have 3 lectures.
Okay, I mean depends also on the energy of the people, because at some one. Okay, okay, okay. Okay, so let's change gears a bit and do some CFT. So right now we have been analyzing some almost geometric analysis of the Feynman diagrams. So now I want to build towards, so we dealt with the tachyon, but there are also these zero modes, okay, in these cases. And that we also need to deal with, like what are these zero modes, what is really happening, and you know. Okay, so a very nice reference for this are a set of lectures that this guy Ted Erler gave at HRI a few years ago, and he wrote some nice lecture notes. So Erler, 4 lectures on open string field theory. So that's some place where you can find some of the equations, and if you want to read more, okay. So now just imagine that there is a DP brane, okay, and for concreteness you can imagine P equal to 3, for example, okay. So what we want to do is we want to kind of consider what are the fields living on the world volume of this D brane, what are their actions, things like that. Okay, so the first thing you do is actually write a string field, this capital psi. What is it? It is the following. It's a vector in the Hilbert space on the interval on the 0 to pi. So it's some vector in that Hilbert space that we were discussing, and it's expanded as the following. So there's an integral dp plus 1k divided by 2 pi to the p plus 1 tk c e to the I k dot x, okay, plus. So what does this mean? This is a vertex operator. So this is an element of this Hilbert space times a coefficient. So tk is a complex number. Okay. So tk is just some complex number, and this c e to the I k dot x belongs to this Hilbert space. Okay. Plus some a mu of k del x mu c e to the I k dot x. Okay. So again, this thing is a complex number, a mu of k, plus I'm not going to write, there are also sort of transverse coordinates. So this mu index belongs to only up to p minus 1. So let's ignore the transverse fluctuation, there is also a term for that. And then there is some beta k del c e to the I k dot x. Okay. So what is this doing is that to each vertex operator there is an associated field. There is the tachyon vertex operator, there is a tachyon field. There is a gauge field vertex operator, there is a gauge field. There is some other crazy vertex operator, some other field. Okay. So we have a DP brane. The momenta are valued in R1 comma P. Okay. And we have this expansion.
So what are we writing? Psi is what?
Psi is so let me write an equation in particle just for scalar that will make it clear. What are we doing? So
Single particle Hilbert space.
this is a single particle Hilbert space, single string Hilbert space. So it's an element of a single string Hilbert space. So just like in a field theory, right? we write usually phi of x, we expand it as dp plus 1k divided by 2 pi to the k plus 1 e to the I k dot x times a k, right? Something like that. So this thing you can write as phi equals integral dp plus 1k a k times k, right? And you get this previous equation just by taking the inner product with x. You get phi of x with this. So this is like the idea that the field operator is an element of the first quantized Hilbert space, and then you do second quantization. That's roughly the idea.
Just the role of the A integration operator is played by a world sheet vertex operator. Is it D?
No. No.
These are what?
So this k, is an element of the single particle Hilbert space. And we know that in a CFT, the states are created by operators. So these are the operators. An operator is a state, so I could write that as a ket if you want. And the coefficient are the fields.
You're talking about is from world sheet state.
Yeah, it's a world sheet state.
Here in this field theory, that's just a particular.
Yeah. Again, think about this, right? These k's could be the world line states. Think of a world line. World line of a single particle. The states are momentum eigenstates. So that's this vector. The coefficients of that vector. So let me not write ak actually. Let me just write phi k because I'm being classical, right? In the quantum theory, it gets promoted to an annihilation creation operator. That's a separate thing. But the action I can write in terms of this phi k as well, right? Just the classical action and the interaction terms. So that's all that is happening here. The only difference in the string is that there are different flavors of these fields. Right? There's not just one kind of scalar field. There's a scalar, there's a vector, there is all host of higher spin fields. So these are exactly analogous formulas. And we are just doing classical stuff. There is no quantum. This is just supposed to represent like, states of the world line.
So the phi k.
Yeah.
Oh, just really, this is not a field.
T of k is a field. This thing is a field. T of k is a field.
So it's some operator, right? No, it's not.
This is the operator. So T of k is a complex number.
Which is the operator?
C e to the I k x.
So shouldn't that be the analog of A then?
I'm writing a classical expansion here.
Okay, but
I'm just doing a Fourier decomposition.
that's fine. But if you, ultimately, let's say phi is an operator in the second quantized theory.
Yeah, so I'll interpret this thing is an operator. If you do second quantization, so this thing will become an operator which creates a tachyon on the D-brane world volume.
So T of k
Will be the operator, which will be the creation operator for, let's say, n equal to 4 super Yang-Mills, right? 0 to p, yes, p. Thanks. Yeah. Yeah, 0 to pi. The sigma that we had for the open string was the interval 0 to pi, so that's why I just wrote it like that, yeah.
And just to know, you said it, but just to
Yeah.
remember, the C e to the ikx or dx mu, that's really supposed to be a state.
A single string state. And I'm writing it as an operator because of the operator state correspondence.
And you will have all such states. In
Everything. So that's why there's a dot.
like level 2, level 3,
Everything. And these don't have to be on shell. I have not imposed any on shell condition, anything. K is a general complex number. K is a general vector in R comma P. Right? Just like here, when you put this expansion, you don't put an on shell constraint on this K.
No, but the operators, the world sheet operators, those are in K's cohomology, right?
Not yet.
Not yet.
Not yet.
So just general.
General. K is completely general.
Not K. I mean those vertex operators. Those are physical vertex operators. Or
No, not physical. So for example, the physicality condition, so QB,
oh, that's the on-shell condition you're saying.
yeah, exactly. So QB on C e to the ikx will be equal to 0 if k square equals 1. Right? But we are not necessarily doing that. So I want to emphasize that these things are completely, the K is completely unconstrained right now. Okay, that's why it's integrated over the entire P plus 1 dimensional space.
So that an E of K will be operators on the brain world column.
Yes.
Exponential IKX can be part of this operator on the merge.
Yes. Yes. Okay, because this is the natural thing, right? So now the action on the D brain world volume will be, for example, have a Maxwell term for this A mu, right? We know that there is a Maxwell theory living on the D brain world volume. So there should be some action that I should write which will give me like Maxwell term for this, maybe the scalar kinetic term for this, and also all the interactions between them or something, okay? So that action is known, okay? So some quadratic action is known for that. But what I want to emphasize here are the fact that when you write this, you only take world sheet vertex operators to begin with ghost number 1. Because they are the analog of classical fields.
Sorry, Raghu.
Yeah.
You said that quadratic action is known.
Yeah.
But can it be written in some nice way in terms of psi?
Yes. So it's just psi, QB psi. So QB is just an operator that acts on psi, it produces a new state, and this pairing is just the BPZ inner product on that Hilbert space. So that Hilbert space has a BPZ actually bilinear form. That is just the action. So you can also see that the equation of motion will be QB psi equal to 0. So this is the action, and the equation of motion is QB psi equal to 0. So this will include as a special case the on-shell conditions, right? This thing is called the BPZ bilinear form. It's like, when you take the 2-point function in a CFT, OI, OJ is some delta IJ over, it's also called the Zama logic of metric or something sometimes. QB is the BRST operator, BRST charge, yeah. C has ghost number plus 1. Yeah, so C has ghost number plus 1 and B has minus 1. So that is why all of these have ghost number 1, because C has ghost number plus 1. Matter fields don't have a ghost number.
Also, when you take this inner product, you have interactions from different sorts of levels as well, right?
Yeah, you can. So you do whatever it is. This is completely well defined. You can calculate. You can literally stick that in and calculate the things.
So you said in particular you get the equation of motion. That is what you get, right?
That is what you get. But I meant that, for example, this one, is not a familiar vertex operator because it has a partial C instead of a C, right? So you will also get some condition on this beta, right? So normally we are not used to thinking of it in this generality, because typically you think your vertex operator is C times a matter guy.
Okay, so what happens then? For
Yeah, so I'm coming.
You can have two C's and one B.
You can also have two C's and one B, yeah. Anything with ghost number 1 is allowed. The only restriction to write a term here is that it should have ghost number 1. Okay, that's it.
Can you explain why is there this constraint?
So this constraint is because of the following. So when you think of just a gauge theory, right? Before you do any gauge fixing or whatever, like in the Maxwell theory, you just have A mu, right? There is no B ghost, there is no C ghost, there is no anything. And that is where you start, okay? But that has a gauge invariance, because of which its propagator is ill-defined, right? The propagator quadratic term has 0 modes. So in string theory, these are those fields. So you should think of these as like the gauge fields and its like kind of friends, which is the initial starting point of your path integral, okay? And after that you identify the gauge transformations, do the gauge fixing, and everything else comes later. Here, just because of some conventions, so I could call this ghost number 0, right? or something, but it's just traditionally called ghost number 1. So in the Yang-Mills case, your fields A mu will be called, let's say, ghost number 1. Okay, I just declare that that has ghost number 1, and then every time you add the Faddeev pop of ghosts to that, you will change the ghost number by something. Okay, but sorry.
Q has ghost number minus.
Sorry.
Q has ghost number 1.
What is Q?
QB.
Q has ghost number 1. So you have ghost number 1, 1 and 1, and that's what you need on the disk. To have a non-zero correlation function, you need ghost number 3. There's a conservation law for the BC ghost system. The conservation law of a BC ghost system is that on a genus G Riemann surface, the total ghost number has to be some 3 times the Euler character or something. Right. It's not 0. So there's a kind of an anomalous conservation law. Typically, you would think that the total charge of anything has to be 0. But for these BC ghosts, the total charge has to be 3 times minus the Euler character, or 3 times the Euler character. The Euler character of disk is +1. Okay, so this is evaluated on the disk.
And psi has ghost number, sorry, 1. So
Yeah.
why does equation of motion has, like, I was thinking equation of motion should have ghost number 0.
Well, now this is a homogeneous equation, right? So whatever you get here, it will literally be some coefficients like this multiplying this. So all of those have to be set to 0. You see, the Hilbert space is graded by the ghost number. So this is something that has ghost number 2. But whatever that state is, its coefficients have to be set to 0. And the coefficients will give you equations just on these t, a, mu, and beta. Right?
Action I, will it have like cubic or higher or
Yeah. So there are some cubic terms. Yes, exactly. Plus interaction terms. But this is the part that determines the kinetic terms and the propagators. Okay. So now we talked about the field. Let's talk about the gauge transformations. Okay. So the gauge transformations are shifts of psi of the following form. Psi plus, sorry, QB lambda. Yeah.
There's no way to formulate a string field. You've basically written it as a collection of particles.
Yeah.
Is there no way to think about it intrinsically as a field valued on strings?
But that's what I'm saying. Like that structure we don't have even after 50, 60 years. We don't have it. Exactly. I mean, not string field. It's saying that we don't understand string theory. Like we don't understand the underlying geometric object of string theory. Like it may be something on loop space or whatever it is. Like it's not been.
Open strings within string field theory is quite explicit in terms of string fields and the psi of.
Yeah. So that I think what Abhijit is saying is that there is one particular example where this interaction term is just like a Chern-Simons type term, some psi cube term, and that's it. So at least in terms of psi, you have a finite action. And then you could imagine that this expansion kind of converges because of L0, and that's fine.
Even when you do the calculations, you don't have to go to that,
To that basis, right?
this basis. Yeah, you can just work with this, as you said, intrinsically.
Yeah.
That's
So
how this solution was written down, right?
yeah, this is Schnabel's analytic solution. Yeah. Right. So the expansion in the Fock space states might not be very efficient, but what you're identifying this psi as an element of the single string Hilbert space. So it's some equation of motion on that space, right? And it might be like a very highly excited coherent state of all of these things. But in most string theories, like as soon as you go to loop level or couple in closed strings, even the action has some infinitely many terms. But okay, so gauge transformations are shifts of psi of this form, where lambda has ghost number 0. Okay, so as already mentioned, QB has ghost number 1, psi has ghost number 1, so this equation is okay. Okay, so these are shifts of these guys, right? So what is the simplest ghost number 0 guy we can write down? We can just take, again, dp plus 1k divided by 2 pi to the k plus 1, small lambda of k e to the ik dot x. Okay. So again, this is an element of the Hilbert space, 0 to pi, and this thing is a complex number. Okay, and there is no c here, so this is a ghost number 0. Okay. Okay, very good. So this is our gauge parameter. Right? This lambda k is really the gauge parameter. Okay, so now we have to see how the shifts come about. Yeah.
Capital psi and capital lambda, everything is a function of ZZ bar?
Well, I'm thinking of them abstractly, all these things are sitting at the origin at some point. But you're right, because I'm thinking of them as vectors in the Hilbert space. And the vectors in the Hilbert space can all be generated by just inserting operators at the origin. So you can think that, yeah, c e to the ik dot x, that operator is sitting at the origin. But yeah, you can also shift it, that will apply some translation operator to it. Sorry. Yeah, it will just rearrange the expansion a bit. Okay, so now, so what does it? How do they shift? So for that, I need to tell you what QB is and how it acts on this, and so on and so forth. Okay, so let me write you the formula for QB. QB is the integral of JB. And JB is C times the stress tensor of the matter sector plus BC partial C. That's it. That's simple in the bosonic string. That's the BRST current. Now, the way you apply QB on some operator is you take the JB of Z lambda 0 OPE and extract the pole term. Right, that follows from general CFT principles. Q is the contour integral of J. You put that next to lambda, you do the OPE, you take the residue of the single pole, and that's the transformation. Okay, so let me write some formulas. So C, so note that this e to the ikx is purely a matter operator. Since it's purely a matter operator, this part is not going to give you any pole. Only this part is going to give you some pole. So C T matter of Z and e to the ik dot x at W has the following operator product expansion. This C of Z, it's actually easy because this thing is a primary in the T. So the primary has weight k square, and then you just have the operator divided by Z minus W square plus the derivative of e to the ik dot x divided by Z minus W, right?
So you are looking at a particular example for lambda.
Yeah, particular example for lambda.
The internally could have the ghost
Yeah,
part, right?
plus dot dot dot.
No, it could also have the ghost part.
It can also, the other terms can also have the ghost part, but the ghost number has to be 0. So it could have things like BC, which has ghost number 0. But for those ones it will, but for this particular one it does not. Yeah, good, thanks. Well, it's an open string, so the weight is just alpha prime k square. So alpha prime is 1. So alpha prime k square by 4 is for the closed string exponentials, These are open string exponentials which have a different conformal weight. Alpha prime is 1, yeah. Okay, so the single pole you can get, note that this looks like a double pole, but this is a function of z. So the single pole term has a partial c k square e to the I k dot x plus I k mu c e to the I k dot x. Right? This partial c came because you Taylor expand this. There's a term that's z minus w times partial c. 1 power of z minus w cancels 1 power, then you get this guy. And for this guy, you just take the derivative and c of z is c of w. Okay. So that's the residue of the single pole. So that's also equal to QB of lambda. Times, I mean, the whole thing should be multiplied with lambda k because, let me write it. So QB on lambda equals integral dp plus 1k over 2 pi to the p plus 1 times this lambda k, okay, and then k square del c e to the I k dot x plus I k mu c e to the I k dot x. Sorry, thank you. K mu del x mu. Okay, so that's what we get. Okay, now good. Now let's compare back to that expansion. We are shifting psi by this amount. Let's first look at this term. What is the term in that expansion which matches this vertex operator? The gauge field term, right? A mu of k. So A mu of k is getting shifted to A mu of k plus I k mu lambda k, right? And the what about the first term? The del c e to the I k x, that's beta. So beta k gets shifted to k square beta of k. Sorry? Lambda k. Sorry, thanks. K square lambda k. Right? So this got shifted, and that's what we have. The first thing is, of course, recognizable. It is literally the gauge transformation of a U1 gauge field. So derivative of lambda. But what you realize is that this thing comes together hand in hand with the transformation of this beta field. Okay. So that's what you normally do. So you use this gauge transformation. No, this is just some beta that I defined there. Use this gauge transformation to set beta equal to 0. Right? Because beta is shifting under the gauge transformation. So if I had an arbitrary field configuration, A mu and beta, I can apply this transformation and on the gauge orbit, find a representative with beta equal to 0. So that is why in the worldsheet you don't see this beta field.
Can you do that in general?
Good. So in general, see, the only point where it will break is when k square is equal to 0. Because then it's not shifting. Okay, that's a special point that you need to take into account separately. But at generic points in k space, you can set it to 0. And that's true for any kind of gauge fixing you do, right? Even things like Lorentz gauge or harmonic gauge, they always fail at some lower codimension locus in your field space, right? Okay, but that's already a good point, because in the case of a D-instanton, you're not going to have a k. but the beta is going to be there as a field, not as a function of k, but beta, and that beta will be gauge invariant. You don't have any momentum. So on a D-instanton, there is no way to set beta to 0, which is sort of, one way to see that they are more special, like, because you just don't have a k, so this thing will not shift. Okay. So on a D-instanton, beta, which is not a function of k, is just a single field, like a single real variable, cannot be set to 0 via gauge transformation.
So are there other gauge transformations because you have other, 3-index gauge fields or whatever?
Yeah. There will be a whole mess. So, there is an infinite number of things here and an infinite number of things there, and they will contribute, yeah.
But none of them will shift your
I think so, yeah. That I think you can just check by some quantum numbers matching, yeah.
Special, it's only as special as making it okay. There's always a mode where k equals 0, which can't be set to 0.
Sorry?
There's always a mode where k is equal to 0, which can't be set to 0 by this.
Yeah. But what I'm saying is that they form some kind of a set of measures 0 among all the modes. When you're doing path integral, it is true that the homogeneous modes of the gauge field cannot be gauge fixed using the standard Faddeev-Popov procedure, which is why the ghosts are massless. Like that's why you have a 1 over k square for the ghost, and you need to have a I epsilon prescription for that. So the standard field theory ghost being massless is a symptom of the same problem. The fact that the homogeneous gauge transformations, you can see here, right? If the lambda was independent of k, you took a mode of lambda k which was just lambda k equal to 0, then this a mu also will not shift. The homogeneous modes of the gauge field cannot also be gauge fixed. Okay, anyway, I will just write the equations of motion and then be done. I don't want to derive it because the derivation is a little bit long. So these are the gauge transformations and the equations of motion that focus on these fields. It's interesting to see them. Is that beta of k plus I k mu a mu k equal to 0. That's one equation. And then the other equation is just the Maxwell's equation.
Sorry to come back to this, but these don't mix with the equations for the higher fields, or you've truncated those fields to 0, or?
I think these ones will not mix. I think because all the other operators also, the vertex operators also get more complicated. I might be wrong about this though, but my suspicion is that it won't, yeah. I mean, okay, if you put the interaction term, of course the equation of motion will change. But I think just at the quadratic order, that's it. So you see, sorry? Yeah. Because so you see you have the Maxwell equation for A, which you should have gotten. And then this saying that, the equation of motion does not involve a derivative of beta. So beta is kind of like an auxiliary field, which is just tracking some k mu, a mu in the thing, right? So you can just set it to 0 in the norm. Right. So that would be like, if you're on shell, it would be like having this is called Lorentz gauge. Yeah.
So for the D-instantons, are you saying that you only have the 0 mode, so you have to deal with this problem, or are you saying these are not globalized at one point, every case?
Not every k. The k here, you see, belongs to R1 comma p. So the p is -1, so the k is nothing. The k belongs to like a singleton set. Yeah. There is no k label for a D-instanton. So I should just drop this integral and remove all the k's from the arguments and drop the e to the I kx. There will also be no mu, so there will be no gauge field because mu is going from 0 to p. So on a D-instanton, you'll just have the first line and the third line. Without any k's.
There's only there's no k label, so it's like you have a k equals 0.
Right. Or it's kind of meaningless to talk about k. That's like the way to say it. So this expansion will be much simpler. It will just have a t c and a beta del c. for a D-instanton. And then T is gauge invariant, beta is also gauge invariant. So you had better integrate over beta, like you better keep it in the path integral because you cannot set it to 0. And that is the problem that the world sheet theory has, as we will see that it does not know this fact that it's supposed to keep beta. Okay, I think we should stop here. Thanks. Euclidean D-brane?
Like in D-instanton, D minus all streaming drops out and higher spin of states drop out because there is no mean.
Yes.
For Euclidean D-brane, you will
Yeah, it will be there. Yeah. It's just the signature will be different, so you'll get some signs in various things. Yeah.